Okay, thank you. So this morning, I'm going to talk about the two-level principle. So we've heard of it, we've heard of it several times already, but it was sometimes mentioned as quote unquote philosophy. But in fact, behind there are just results. And so you can say that even that principle is vindicated. And I'll talk about, about there are several, actually several versions of it. So I'll talk about four versions. First, let's call it infinitesimal braid version, which is due to Ihara. Then more generally say not more generally, sorry, I shouldn't say that. The genus zero version. Then Grothendieck original intuition, which I write pi 1 of m. So this is symbolic. I mean, I'll explain. The pi 1, the fundamental group of the moduli space is equal to the fundamental group at infinity. But of course, I mean, right now it's just symbolic. And the fourth one is the one we have with Leila, which is, let's maybe put it this way, which means the Pan's complex is simply connected. So I insist that without the two-level principle, there would be no Grothendieck-Teichmüller theory. Well, you've heard Florian yesterday. So what he explained is that if you have a sufficiently large sample of a variety, then you take the geometric pi 1 as a functor. Then you take the automorphisms of the functor, automorphism meaning invertible natural transformations. And then the invertible transformations, the automorphism of the geometric pi 1 functor will equal the Galois group of the base field in certain good cases. Then there are even two addenda, which is one, you don't need the full information, you don't need the full geometric profinite groups, you need much less. And the second is you should take the field to be, say, a number field. And you need far less varieties as a sample than all varieties. For instance, if you take all the arrangements of lines in P2, that's okay. So he took arrangements of lines which contained the lines which define M05, but you can take, say, just all the arrangements of lines in P2 and a very tiny quotient of the fundamental group, and then the automorphism group of the geometric pi 1 functor will equal the Galois group of, say, Q, if you just start with Q, and rational arrangements of lines. So here, as he mentioned also, and the big problem is that by contrast, we'll be able to sort of write down an explicit form of the Grothendieck-Teichmüller groups and several versions, but we don't know whether it's equal to the Galois group. But we couldn't write anything. I mean, we couldn't write explicitly the Grothendieck-Teichmüller group, or there wouldn't be anything like that if there were not the two-level principle. So the two-level principle is the primal intuition, the original intuition of Grothendieck, and that's why everything works. I mean, not everything works, but that's how you can write a group with a finite number of equations, actually 3, and with Leila with a new group with 4, but just a finite number. And it was say in genus 1 pro-unipotent, thanks to Hidekatsu's results. You just need the pentagon. So the first, I'll be a bit sketchy on this, and I'll try to explain essentially this, which is in the esquisse. Huh? This is the esquisse. This thing is the esquisse. So let's start with the infinitesimal braid version. So you've already heard about it, so I will be very quick. So there's a very nice paper by Hihara, which is Israel Journal of Math 1992. So you start with P5, which is the braid group on 5 strands on the sphere. So 5 strand spherical braid groups, spherical braids. Then you go to the corresponding Lie algebra. By the way, what do you call the corresponding Lie algebra? Just a word. If you have a group, say an algebraic group. If you have an algebraic group, you have a Lévy decomposition. So you have a reductive quotient. The reductive quotients of all our groups are very simple. It's usually just the multiplicative group. And then you have maximal pro-nilpotent quotient, pro-unipotent quotient. And pro-unipotent groups are, the category of pro-unipotent group is equivalent to the category of its Lie algebra. That's Quillen. So when we write something like this, so that you complete, you take the maximal pro-unipotent ideal, and you take the Lie algebra, and you take the graded parts. And you take the associated grade. So these are called infinitesimal braid. Braids. The reason I prefer this name other than Kono-Drinfeld is that because there is a theorem which says that this thing is one formal, or actually filtered formal. So this is a pro-unipotent. This is the completion actually. Okay. So everywhere it's profinite. It's pro-unipotent completion, and this is Kono-Drinfeld. I prefer to call this theorem the Kono-Drinfeld theorem, namely braid groups are formal, and they're formal via associators. The associators which give the formality to isomorphism, and so I prefer to call the theorem Kono-Drinfeld, and these are the infinitesimal braids. Anyway. Yeah, everything is completed. I said it, sorry. Everything is completed. I just don't write the completion. So Leila wrote the presentation of that group. So essentially, so this is, you have the xij's, xii equals 0, xij equals xji, and then you have the sum of, so I take, here for the time being, I take n to be anything, and I take Pn. I mean, I take n anything, not 5. I don't need 5, sorry. Well, yeah, for the time being, I take n, just n strand. I don't need 5. This is true for all n anyway. Well, xij, xkl equals 0 for ij intersected kl different from 0, and the generators are this, and the grading is that the degree is 1. So for instance, you see that here xij, xkl, they commute whenever whenever ij and kl are disjoint, but they could intertwine. Okay, you could very well have, I dare not draw, because if I draw it will be a mess, but sorry, you could have x, you could have 1, 2, 3, 4, for instance, and this is ij and this is kl. Why? Because if you take the bracket of these of x1, 3 and x2, 4, the bracket in the Lie algebra will have a grading which is larger, which is 2, not 1. So when you take the graded version, you get 0. You see? I mean, I'm just saying that, well, I'm saying what's written on the board, but it doesn't mean that they're far away. Anyway, then you have derivations, and then you have what are called, there's so many things to say, sorry. I cannot spend too much time. Derivations, so d of xij, and these are tangential, reciprocal. There are many words. Special equals inertia preserving. Derivations, so it's d of xij equals xij times something. I mean, you give yourself a something. And these are derivations. So derivations of why do we take this tangential, etc.? It's because as somebody mentioned it, maybe it's Leila, the Galois group preserves inertia groups. So this is the trace, the distant trace of the fact that you preserve inertia groups. This is very important. There's a long story behind. I'm not going to go into it. The long story behind starts with, for people who like number theory, I mean, everybody likes number theory, people who are more expert than I am in number theory. It started with Neukirch, and the Neukirch understood how to recognize the Galois group of QP up to conjugacy group theoretically inside the Galois group of Q. So the very basis of abelian geometry is to recognize inertia groups of ideals of the Galois group of a field inside. This is birational abelian geometry inside the full Galois group. So this is very important, but okay, let's do it. And now okay, I have to be. Sorry? I'm not going to talk. It's 69. You ask. Maybe you knew Neukirch. Maybe Dinesh knew Neukirch. No, it's a long story. It's a very long story, and it's completely disjointed with this. But as somebody mentioned, it's really Neukirch, Uchida, or the forefathers of abelian geometry. So you have these derivations, and the long and the short is that you prove that if you call Dn equal the Lie algebra, they form a Lie algebra. They form a Lie algebra because you can take the bracket of two derivations. So if the Lie algebra of derivations of tangential, say, of special, here I call them special, tangential derivations of the n, then dn equals d5 for n larger or equal to 5. Sorry? Yeah, you have the action of the, yeah. And okay, yeah. Maybe, yeah, there is an action of the symmetric groups with sigma ij equals x, sigma minus 1i, sigma minus 1j, with sigma. Sorry?
You must take invariant.
I must take, this is the SN invariant. SN invariant of SN tangent, SN invariant. Sorry, I'm trying to say things a bit fast. There are many, many things you can say. So, and there are other results, but the thing which is important here is that it stabilizes, okay? And it stabilizes at n equals 5. N equals 5 because it's dimension 2, M05. So, so there are other things to say, and Hiara's paper, which is one of the founding papers in the domain, is really, really important. But so let's go to, because we don't have much time, let's go to genus. So genus 0. So what does genus 0 mean? It means that I write genus 0 because here I will go to any genus and any, so this refers to moduli spaces of curves in genus 0, which simply means P1 with n marked points. So in genus 0, there are many, it's a big dictionary, it's a fairly long dictionary of essentially equivalent ways of saying things, but the dictionary is not trivial. So there is a geometric dictionary and there is, you can say, category theoretic dictionary or whatever. Let me try to give you just the gist. So the gist is that the two-level principle is basically equivalent here to the Mac-Lane relations. So what does it mean? Let me put it the way Drinfeld puts it. So you take a, and I'm not going to define it because it would be too long, a quasi, how do you call them? Quasi-Hopf algebra. I'll write them down. I don't know. Probably did. I'm not sure. You never know what Grothendieck-Teichmüller. That I really don't know. I don't know. I'm not sure he made the connection. No, because this, what he says in the Esquisse is really this, which as usual is very Grothendieck, that is much more general. And I'm not showing you what happens, in fact, in genus 0. So let's say, well, quasi-Hopf, and you have to say quasi-triangular. But the long and the short have to quasi-Hopf, quasi-triangular Hopf algebra. The long and the short is that, let's call them, I don't know, mod A, which are the A modules, so equals the representations of A. The category of representations of A is a braided category. And what does it mean? It means basically, so again, I give you only the gist, is that you have a, if you have two A modules, then you have a tensor product. Then you have a commutativity isomorphism. And you have and that's a new thing. The really new thing is that you have a that's what Drinfeld insisted on, and that's the whole point in some sense, in genus 0, is that you have an associativity isomorphism functor. So you have, so A and C, which does this. And this was, until Drinfeld came, this was more or less taken for granted. That is, people would not so much look at this, at the associativity. Let's say A was just the natural, or the trivial associativity. Now, so now you have these two functors actually, so these which actually they depend on your representations, but I mean no, the way I put it, they should depend on the representation, but that doesn't matter. And so you have braid. So how do you? So if I have, so I do the same drawing that Benjamin drew yesterday. So pictorially, you have A and C. So you have U, V. So here it goes from U, tensor V, tensor W. Here it goes to U, sorry, tensor V, tensor W. Here it goes from U tensor V to V tensor U. And you have braids, which you can say that sigma 1 is C tensor 1. So if I have a three braid group, so I have three UVW. So sigma 1 is C tensor 1, and sigma 2 is A minus 1 tensor C, A, which means you start from A tensor W, sorry, tensor V tensor W. Then you first do A, then it shifts your bracket. Then you, because the rule is that, oh, sorry, it's 1 tensor C. The rule is that you can only permute things which are inside the bracket, okay? So here you first do A, which shifts this to U tensor V tensor W. Then you can do C, which shifts V and which permutes, swaps V and W. And then you do A minus 1, and then you go back to here. No, sorry, you go back to, no, you've shifted V and W. You've swapped V and W. Okay, so you have sigma 1 and sigma 2. And Drinfeld's main idea was that, no, I shouldn't say main idea. There's too many ideas in that paper. It's inexhaustible. But one of the ideas are the core ideas to define the Grothendieck-Teichmüller group is that you can map C to the lambda and A to the F of sigma 1 square, sigma 2 square. So this is slightly symbolic, but you can, I mean, I almost gave the right definition. So again, the point is that for C, there is not much you can do because it's a braid group on 2 strands. So it's Z or Z hat or Z, yeah, Z or Z hat. And on A, you can do A goes to AF. Now, of course, you should recognize what we did in P1 on P1 minus 3 point, where you have X goes to X to pi sigma. Sigma is in this time in GQ, or even, yeah. If sigma is in GQ, do this, and P goes to P F sigma X Y. X is sigma 1 square, Y is sigma 2 square. So this should remind you of this. This is the same thing. Oh, so in this context, if you start by saying that lambda is an integer and F is also an integer, so nothing happens. That is, there are no. Oh, sorry. And sorry. X equal.
Y equals A squared A minus 1. Just make the y half.
Say it again.
I think to connect AC with XY,
Yes.
you want to write X equals C squared.
Yeah, X equals C squared, but it's the same. It's on 3 strands.
Yeah, and Y equals A squared A minus 1.
Yeah. Well, yeah, but that's what I wrote. It's because here I wrote this. You remember that you had y was equal to p minus 1 theta of x t. And this is the same thing as this. Let's say the longer, it's better to say that A goes to P. Yes, absolutely. Exactly. Yes, deformations if you want. Yes, but the next idea, well, so first, what should they satisfy? What should these things satisfy in order to define another braided category? The Maclane relations. And that's where the Maclane relations come. So Maclane's relations, maybe I write the pentagon. So the pentagon is a bit long, but so Maclane's relations. So Maclane in the 60s wrote the defining relations for braided categories. And there are 2 hexagons, which I don't write because it will be too long, plus 1 pentagon. Let me write the pentagon. So the pentagon is V1. I don't know if I won't put tensor products because it's really too long. V4, 2, V1, V2, V3, V4. 2, V1, V2, V3, V4. So I'm just moving around the bracketing pattern. V1, V2, V3, and then I'll explain if need be. V1, V2, V3, V4. And here, see this? So this is the pentagon. This is Maclane's original pentagon. It's early 60s. So here you should restore all the tensor products, and the rule is that you're allowed to shift or to displace brackets only if I mean, you consider what is in a bracket as a packet. So you're allowed to do this, and this is your pentagon. Pentagon means that if I replace C by this and A by this, so pentagon is only about A. There are only A's. So here there should be indices, but there are only A's. There are no C's. And if I replace like this, the pentagon should still commute. So the 2-level principle here is given by the Maclane's relations, which are 2 hexagons plus 1 pentagon. The hexagon involves three spaces, but 3 modules, but they involve 3 strands. So the braid group on 3 strands, and the pentagon involves the braid group on 4 strands. Now, just be careful. We're talking about plane braid groups. So plane braid groups on 4 strands corresponds to spherical braid group on 5 strands. So that's why here you have only 5. You should imagine that there was one strand at infinity, quotient. So this is why you have only 4 strands and not 5, because it's plane and not spherical. So the second And Drinfeld's a version of the two-level principle is that deformations of braided categories are governed by Maclane's relations. Maclane's relations involve only the first two levels. The first two levels meaning simply meaning that it involves 3 and 4, the braid groups on 3 and 4 strands. Then from there, Drinfeld derived the relations. We always say relations, but they are really equations for the defining equations for the Grothendieck-Teichmüller group. Now there are many. Well, that's what I said. 5, because Ihara works on the sphere, and on the sphere, the 5-strand braid group on the sphere corresponds to a 4-strand braid group on this plane, because there is a strand at infinity, which is not involved. You can always have one at infinity, and it's not involved. So there are 2 types of translations. One are the algebraic translations. You can say these things in many, not many, but just 2 or 3 different ways using, then you have cabling, then you have co-simplicial structures, you can have operad algebras. So you have several, say, ways of phrasing this. And as what Benjamin did yesterday is that he showed you this Lie, so the Kono-Drinfeld theorem. So Kono-Drinfeld theorem, where here it's completed, here it's completed. This is the formality isomorphism. On this side, you have the operad of parenthesized braid, and on this side you have what's your notation for the chords? The chords. The chords, the infinitesimal chords. The chord diagram, les diagrammes de cordes. PAC. So yeah, so what he showed you is this actually. CD, like a small or big one. Yeah. Here, the parenthesized braids, this is very much like this. This is and the chord diagrams I haven't shown you. Now there are also there's the geometrical, more geometrical approach, which says that, and these are translations too. These are translations too. When I write this is not just an analogy. This is just a sort of a translator. Let's say it's one of the entry of the dictionaries. So the dictionary is, well, for instance, to give you one entry of the dictionary, you have, I'll talk about moduli spaces more generally in 5 minutes. So you have these spaces, which are the classifying spaces of sphere minus endpoints. Now this can be compactified. It's interesting because in this theory, you always have a problem with the bar. There are two kinds of quote-unquote compactification, passing to the algebraic closure and passing to a compactification in the sense of topology. And in some sense, these are two compactification, quote unquote. But here it's just a compactification. So it's called the stable. Let me write G, and I'll explain more if stable completion or compactification. So this is Mumford, and there's Deligne, Mumford, and this is Deligne, Mumford. So this is the stable completion. But the stable completion in genus 0, this can be, so it has a boundary. The boundary is a normal crossing divisor all genus, any. And in genus 0, you can really rather easily describe this. What do you do in order to compactify your moduli space? You add surfaces with nodes if you work over, so that's Bayes, if you work over complex numbers. And what do you get here? Suppose here, you should, at the boundary, what you get is you blow ups, you do some blow ups, and you get chains of P1s. So of copies of P1. So for instance, for n equals 3, n equals 3, you cannot do anything. So I write it this way. And this you know, because M0 is 3 at 1 point, so there is not much you can do. For n equals 4, what you do is you have this. So I can write at 1, 2, 3, 4, but I don't even write 1, 2, 3, 4. There are 4 points. So what does this mean? It means that you have 2 copies of P1, which cross at a certain point. And why is it stable? To be stable means, which is a very Indian notion, because it was introduced by, in a slightly different context for fiber bundles, but it was introduced by Narasimhan or somebody like this, by Seshadra Narasimhan. And to be stable means that you don't, means that exactly means that the automorphism group is finite. The automorphism group of the structure is finite, and that exactly means that you have at least 3 points on every P1, 3 distinguished points. So here you have the number of points, and here you have an intersection. So that makes 3 points, 3 points. And what I will draw very quickly, all too quickly, are not all of this, because this is big. This has components of every of all dimensions, but I'll draw the maximally degenerate points. So the maximally degenerate points are chains of P1 minus 3 points, or not minus, with 3 distinguished points. And I will do this to show you what it's like. So for n equals 5, you have only one possibility, which is this. And for n equals 6, I'll stop here. It's I'll stop here. It's the first time that you have 2 possibilities, which are like this. So one is like this, and and you have 2 topologically different possibilities, and the other one is like this. So you see, you have 4 copies of P1, which intersect, and on each of these copies, you have 3 distinguished points. Here, for instance, you have 2 mark points and one intersection. Here, you have 3 intersections. So whatever. No, 6. Non, pardon. Non, oui, alors, oui, là, sorry. Okay, so all I want to say here is that there are many translations. No, not many, again, no, it's a dictionary with maybe 6 or 7 entries. And the 6 or 7 entries, I could write as, I don't write them, I mean, it would be much too long, but you can find them in, for instance, Panorama et Synthèse, which we wrote, I don't know, at the end of, somewhere after the war. And it's also in, I think, in other places. So now the exercise is to give translations between, for instance, this and braided tensor categories. So the upshot is that genus zero, the genus zero theory, say, has a big advantage that everything can be done more or less explicitly. For instance, here you can describe this divisor at infinity, normal crossing divisor at infinity, in a very explicit way. That's Kontsevich likes to describe it with bubbles. Okay, bubbles because you have P1 minus 3 point is like P1. I mean, P1 is just a sphere, so it's a bubble, and then you have accumulate, and you can accumulate bubbles, and so you can either instead of this. So I didn't want to write it this way because it's too difficult to draw, but instead of writing like this, which is just a line, a projective line, then you can write a bubble and you can draw a bubble. So you have the bubbles, you have this, you have the braided categories, you have what we call bracketing patterns, you have what Hiara used to call points with increasing degrees of intimacy. So if you put points on the line and you have a sort of tangential base points, but anyway, all this you can find on old text, which we can give the more precise references. Now, Grothendieck was, as usual, it's the eagle story. He looked at everything with an eagle eye, so maybe not so precisely, but from very far up from the sky. And now I'm going to tell you how you can vindicate what he says. So it's P, the pi one of them. So let me talk first of all. So M is for MGN, G and N for 3G minus 3 plus N bigger than 2. And the two-level principle is here. So let me write MGN. So I'll show you what that means, and I will even prove it for you. So what does he mean? So first, that's what he says. He says, so by the way, so he says, all this, so he said the Teichmüller tower can be built with the first two levels. So the first two levels are the levels for this equal 1 and 2, and they're 0, 4, 1, 1, 0, 5, 1, 2. But 4 points on the sphere is quote unquote, I shouldn't say that in front of this audience, but it's almost an elliptic curve, because if you have an elliptic curve, you take the Weierstrass points, and then you just have the how do you call it? The elliptic involution. And this is the same because you can arrange that the 2 points are swapped by the involution. And the next I should say that the next level is 0, 6 and 0, 6 and 1, 3. No, is it 1, 3? I'm so used to this. I mean 0, 6 is 6 points. So level 2, so this is where we are going to talk. 1, 2, and 3 levels, 1, 3. The third level is still reachable. Nobody talks about it because of what I will tell you. But the important thing is, no, and 2, 3G, sorry. Yeah, and there is 2, 0, yeah. So what is important is that 0, 6 is almost like 2, 0. Because again, every curve of genus 2 is hyperelliptic. So you take again the ramification points of the hyperelliptic involution, and this is almost 0, 6. But then real Teichmüller theory, for people who are complex, who do complex analysis, or those who do geometry, it starts here. It started with M1, M3. Usually you don't write n when it's 0. So M3 is the first mysterious object. But okay, here, what does it mean? I mentioned who?
You mentioned Torelli's theorem, but there is no difference in Torelli with genus 3 or genus 1, 2, and so on.
Yes, there is, because
Canonical curve, there's embedding or not, that will depend on hyperelliptic or not.
yeah, but it depends whether Torelli map is surjective or not.
That is.
I mean, for what we're doing, that's one. Okay, that's one. That's a little bit philosophical, but not so much. Is that we're doing what Grothendieck was trying to do is to do something which is very different from what you do with a billion varieties. So if the Torelli map is surjective, then the curve and its Jacobian are more or less the same. So the best.
My question is it genus 3 non-hyperelliptic
No.
and hyperelliptic?
Yeah. Everything together. Yeah, hyperelliptic is codimension 1, and yes, it's everything together, which is difficult. It's the non-hyperelliptic.
Hyperelliptic is the what you're saying.
Yeah. It's here. It's that you start having non-hyperelliptic curve. Yeah, and that's why here it's also the Bas-Meineke-Serre theorem that we mentioned that tells you that for a billion varieties, the Galois action is poor. I mean, it's not very rich. It factors through the cyclotomic character. So what Grothendieck was doing, it was really trying to tackle the curves and not their Jacobians, not a billion varieties, if you want. So now you have, okay, so now you have MGN. Well, it takes hours to actually build this space as a what if you are, so you have several versions. The version over C is BS, basically. I mean, the compactification is BS, and it's Horvitz, and it's. So this is, and the version over Z is much more difficult. So I don't know. I mean, I think you can say it's Deligne Mumford. And so there is a version over Z. I mean, it's actually one stack over Z for algebraic geometry. And what we're doing is we're in Grothendieck-Teichmüller theory, we use only the generic fiber of MGN viewed as a stack over Z. So Grothendieck-Teichmüller is only preoccupied with this. I mean, dealing with this. So now you have MGN, which is again, so SGN equal the surface. There are theorems everywhere. Surface of genus G. So surface for, so it's a differentiable. It's, what is it? It's differentiable, orientable surface of genus G and holes, call it. So marked point. Cusps. So be aware that there are everywhere theorems which are, that's really interesting. There are everywhere theorems which are far from trivial. Like for instance, here you say, why there is only one, I mean, all differentiable surfaces like this are actually diffeomorphic. So there is no, for instance, wild phenomena in dimension 2, in real dimension 2. For instance, you can say that you can write in this, you can work in a C0 and C1 category. That doesn't matter. If you're an algebraic geometer, it's much more complicated. Anyway, I will write simply S equal SGN. And it's, oh, okay, and hyperbolic. So hyperbolic means 2G minus 2 plus N positive. M of S, okay? What is it that happens? Okay, you have Teichmüller space. And so this is the Teichmüller space of your surface. This is a moduli space of your surface, which is the classifying space of the say, complex structure on this object. Teichmüller space is an intrinsically analytic object, because on top of everything, you have complex analytic, real analytic, and differentiable, say. So this is a complex analytic object, which does not exist for algebraic geometry. This is a stack. So this is an unramified Galois cover in the sense of orbifolds. I mean, maybe Leila alluded to it, in the sense that it's not unramified in the usual sense of the word, because there are surfaces, there are curves with automorphisms. So but it's unramified in the sense of stacks, or in the sense of, here in the sense of orbifolds. And it's a Galois unramified, infinite. It's a Galois stack unramified cover with group gamma of S. So gamma of S is the pi1 of the moduli space. And it turns out that it turns out this is the way it was defined. It's also the pi0, the homotopy classes of the diffeomorphism of the orientation preserving diffeomorphism of your surface. So all of this, of course, it takes a long time to really talk about. So what do you do next? Next, you say, okay, I have 7 minutes, trying to fit something in 7 minutes, to explain this in 7 minutes. So this, what happens at infinity? At infinity, you have what since Bears we call nodes, what are called cusps, and okay. So referring to what I did last time, what you do is, what happens is, when you go to infinity, there is one geodesic, at least, which is shrinking. So what you get is something like this, and here you get the rest of the surface, and here you get the rest of the surface. So this is codimension 1. This is on the divisor. So I'm trying to describe the divisor at it's the divisor at infinity of the stable completion. But what happens when you go to infinity on moduli space is that at least one geodesic goes to 0. So the length of one geodesic goes to 0. What does it mean? It means that on your surface S, there's one metric of curvature -1. If you give yourself the complex structure, you give yourself AO ipso a metric of curvature -1. And when you go to infinity, at least one geodesic goes to infinity. If there is only one, actually the number of 0, if the number of geodesic which go to 0, the length of which go to 0, is exactly the codimension of where we are on the divisor. For instance, if only one geodesic has a length which goes to 0, then you are in the codimension 1 part of this. But here you have a normal crossing divisor. Actually, it's not even, you have self-intersections. Okay, I'm not going into this. But you have at least one geodesic which goes to 0. Now let's write m epsilon to be equal inside m to be that part of n which has at least one small geodesic. So m epsilon equals how do I write it? So there exists a geodesic gamma, so L gamma is smaller than epsilon. So for epsilon, small positive. So how small? Small. How small? Exactly as small as I said last time. Last time I told you there is a universal constant. There is a universal constant, call it mu, such that if the lengths of two geodesics, both lengths of curves of the geodesics are less than mu, then they will not intersect. So you take epsilon to be smaller than this thing. So you're sure that if you have short geodesics, they will not intersect. So you take this. You take this. So this is at infinity on moduli space. Now m minus m, this is compact. And the length, and and m is let's say it's a direct limit of these things, of these compact sets. I'm a bit okay. I'm going too fast, but okay. I mean, these compact sets will grow. So I don't know how to. You cannot draw it possibly, but okay. And now you have m minus epsilon. Here you have epsilon. So actually, m epsilon could be thought of as a tubular neighborhood of the boundary if you know about this, which is complicated. It's the Beers or Deligne-Mumford completion of it. So you have this. And so m is this. So pi1 equals, so what does this mean? What does this mean? It means that the theorem is that pi1 of m epsilon equals pi1 of m for all epsilon. If and only if the dimension of m is bigger than 2. So this is what you should understand in the esquisse. Of course, this is more or less put this way, but from an eagle's viewpoint. And why does it have anything to do with the two-level principle? This is because of what the divisor at infinity is like. What is the divisor at infinity made of? It's made of so if m equals mgn, the divisor at infinity is made of other copies of the moduli space, spaces of strictly smaller dimension. Why? Simply because at infinity, you simply add this, and here you have two surfaces, and 3g minus 3 plus n decreases when you sort of cut a node. So here you have, for instance, at infinity, you have one component, which is the product of these two moduli spaces. Okay? So, and these have strictly smaller dimensions. And what this says is that actually what you can do, it's a dévissage, as it says. What you can do is the pi1 of this is the same as the pi1 of the divisor, but that doesn't mean anything because the divisor is normal crossing, but it's not a normal variety. So you have to have I mean, Goncharov explains it. You have to have a simplicial variety. You have to imagine that this is a simplicial variety, actually. And but anyway, you're reduced to the first two level because here you have two. So that's Grothendieck's viewpoint. Huh? Okay, so it's and you can do something with it. I mean, but how do you prove this? And I won't give you a proof, but if I can, okay, if I have 2 minutes, I tell you just what the proof is like. The proof, which is not proved by Grothendieck, he says, I don't have the tools to do it. And yes, he didn't have the tool to do it because you have to use Thurston, Wolpert, and Harer-Ivanov, all of them proved theorems basically at the same time, 85, 86. And that's the theorem you use. So if you use these theorems, you'll prove this. Well, how do you prove it? Then you what is dm epsilon like? what you do is that it's easy to see what dm epsilon is like. So dm epsilon is inside the moduli space. So it's essentially like the boundary of the moduli space, but it's inside. And dm epsilon is a bit difficult it's difficult to understand. But if you lift it to t, so you just take the pre-image by this, then you do understand what it is, because using Fenchel-Nielsen coordinates, you understand that it's exactly like the curve complex. The curve complex, maybe I'll try to define it tomorrow, but certainly Leila will have to define something which is like the curve complex. And so what you want to prove actually is, so the real theorem is dt epsilon is simply connected if and only if the dimension is bigger than 2. And here you use a theorem which first you understand that the pi1 of the curve complex is homeomorphic to the curve complex. Sorry, this is homeomorphic to the curve complex. And the curve complex, this is one of the, I would insist on it. The curve complex showing finding the homotopy type of the curve complex is one of the very important results of the mid-80s. And this was done by Harrer on one side of the Iron Curtain and Ivanov on the other side. They didn't know each other. So they proved that it's homotopic to a bouquet of spheres. And among other things, this is true. Once you've done the identifications and so on. So the homotopy type of the curve complex, finding the homotopy type of the curve complex is a real important thing, because, for instance, the well-known Madsen-Weich theorem, it's the main ingredient. So it's the main ingredient of certain results, certain more or less recent results, including understanding the stable cohomology of the moduli stack of curves, including the results in K-theory. So it's a very important core result. And this is exactly what you use here. So it was proved in 85, 86, so just right after the Esquisse. And you have to use also results of Wolpert. Wolpert did some wonderful things about, for instance, the symplectic geometry on Teichmüller and moduli spaces. Okay, well, that was much too short, but I tried to pack too much. Thank you.
Are there any questions?
Sorry? Yes? Yes. Elliptic curve, what you call normally elliptic curve, that is, you take the origin as a mark point. You know, people say elliptic curve as opposed to genus 1 curves, but elliptic curve, so you have an origin, so the origin, the mark point. So this is hyperbolic because it has Euler characteristic -1. And it's very much given by the Weierstrass point. So they're from the point, for instance, from the point of view of complexes of curves, the complexes of curve of this and this are simply isomorphic, and same thing here. So there is no difference.
So, but how do you go from genus 0 to genus 1? I mean,
you don't go. No, I'm only saying that if you have an elliptic curve and you take the Weierstrass points, then there only remains to know there only remains to add the elliptic involution to get your curve. So it almost defined the curve.
Yeah,
if you're naive like I am. I guess for an arithmetician, it's not quite true. But geometrically over C, it's true.
So I have a question, Pierre. Just like maybe it's technical, but epsilon should be less than mu, right? On
Yes.
Even on the non-equivalence, right?
Oh,
When you say the pi one-
yeah. Well, yeah. Well, it means the interest is when epsilon goes to
Yeah,
zero.
okay.
So epsilon, yeah. But,
Okay.
but the point is to let epsilon goes to zero, and the real point, and the point is to just to see that if you have t epsilon and m epsilon, the power of this, the pi one of this will be equal to this, if and only if this is simply connected, and this is simply connected, if and only if, etc.
Yeah, and also I understand that you say that algebraic geometry becomes like non-trivial for genus 3. Or,
No,
genus
it's
3?
not algebraic. Well, maybe it's
I mean,
algebraic.
just like general idea, but it's level 6 for 3-0. So it's the level 6 for 3-0. For the
3G.
and so what happens for
no,
level?
3G. Yeah, it's level. Yeah.
And so what happens for 4 and 5?
For instance, I'm not talking about it, but actually, what is important is the genus, not the number of mark points. Well, you have also, maybe somebody said it, you have also, if you forget the first, I think Benjamin said it, if you forget the first m mark points, then you have this forgetting map. And here you have the configuration space of m points on a sphere, on a surface of genus G. And this has been studied very deeply in the Japanese school by Hiroaki and other people, but of course not from a topological viewpoint. So the difficult thing is to change the genus. E.g., the congruent subgroup property is true for G equals 0, 1, 2, and then we don't know any n. E.g., we don't know if the center of this completion is trivial. This we don't know, etc., etc. I mean, it's everything. Oh, gamma 3 is the mapping class group of genus. It's this gamma. It's the Teichmüller group or mapping class group in genus 3. Let's say for people who do either complex analysis or Teichmüller theory or things like that, genus 3 is the, and I like to imagine that this is very good for PhD because hyperelliptic things are reachable, but very technical. And usually people don't bother to study them.
Again, so back on this question, so you say that we have two-level principle, so we did level 1 and 2. Okay, so why do we want to say about level 6 exactly? So
no, I shouldn't say level 6. I should say that it's genus 3.
Then what
counts is the genus here. I mean, it is true. Here it's true that it's level 2 in the sense of 3G minus 3G plus 3. It depends what you're doing. Here it's true. The two-level principle is this, really. But the fact is, adding mark points for many, many things is not such a problem. But changing genus is because of this. But changing the genus is much more difficult. For instance, when you try to compute it was a very well-known result by Matz and Weiss that they computed the stable homology. Then you take everything of type G1, so you take this. This large G and only one puncture. Also, it's nice when you take one. The easiest thing is always to take exactly one puncture, because then the curve is affine and you're not bothered by braid groups. Okay? Because the pi1 of this is the braid group phi 1 of this is the braid group of genus G on n strand. Oh, sorry, well, M maybe if I write that. So you don't want to be bothered by braid groups here. I mean, if you do this, and then you let G goes to infinity, and you ask yourself, what is the cohomology of MG1 with coefficients in Q when G goes to infinity? And the answer is a very well-known theorem, and it's also used by people in, I don't know, mirror symmetry and everywhere, that you have only the tautological classes. I mean, there was a guess by Mumford, very educated guess by Mumford many, many years ago, and it was vindicated not so long ago. But yes, I mean, it's increasing the genus, which is really difficult in this thing. Mm-hmm. So now, just as a, well, no, forget it. Yeah, in conclusion, I would say that the pro-unipotent theory is very, of course, very interesting, and it has many, there are many tools you can use. And here you use completely different tool. That was 25 years ago, and since then there are other things which have been done, which I did. But the toolbox is completely different. I mean, you don't have homology, cohomology, etc. I would dare to say that probably what Grothendieck had in mind, if he had anything in mind, because his mind is very big, had more to do with this in the sense that he probably didn't know too much about multiple zeta values, or he didn't know anything about multiple zeta values, and he had more. This is very quote unquote nonlinear. It's so nonlinear that linearity does not exist anymore. So you don't have homology, cohomology. You don't have functions even. You have to do something really different. So the next steps are curve complexes, and the step after is completed curve complexes, and the step after is string topology. And so there are several steps after that. That's from 1995, 97.
Yes.
Okay. Well.
Okay, so thanks, Speaker One.